Okay, so hello everyone, my name is Vijay Mukherjee, and we will start this session now. So I'm a research scholar at IIT Kharagpur, and I will be conducting this live session for NPTEL course on computer organization and architecture. So as usual, we'll be solving some basic problems, which will be asked in your assignments and exams at the end. So the session is being recorded, so it will be available on YouTube. Also, it will be interactive, so you can ask questions or any doubts regarding the problems that we are solving in the chat. I will respond to them. So let's start this week's session. So this is the first question: which of the following statement is or are true? Number 1, option number A: in memory, data are stored in the form 0 and 1. Option B: memory system stores data and instructions. Option C: every bit of memory has unique address. And option D: all of this above, all of this. So can you guess which of these will be the answer? Anyone can write in the chat what will be the answer. No, option D is wrong. D is wrong. Okay, so option A is correct, right? Option A is true. Memory data are stored in A and 0 and 1 form. So option 1 true, because in memory we know in computer it only understands binary language, so data are stored in 0 and 1. Now in case of option 2, it is also true. If you know the memory contains both data and instructions. Now coming to option 3, it is said every bit of memory has a unique address. This is not correct. Every memory location has an address. Every memory location has an address. Suppose this is the memory and these are the locations. So these all have unique address, but inside it can be, suppose, 16-bit memory. Each bit of this memory has not unique address. It has to be addressed using this. So option C is wrong. So correct answer is A and B. Right. If you have any doubt, you can ask. I will respond. Okay, so let's go to the next question. So consider a memory with n address lines and m data lines. What will be the total number of bits in this memory? So suppose this is the memory and it is given bit address bus. Also it is given there are m data lines. Also it is given there are m data bus. So if there are n bit address, if an address is n bit, so how many bit it can like how many memory address it can represent? So it will be 2 to the power of n. So there are 2 to the power of n. If there is n bit bus address, then there will be n bit address locations, right? N 2 to the power of n address location. Now the each so now it is like, so we can write a summary like this: n address line means total there will be 2 to the power of n address location. Now m data bus means each address location will have m bits. Each address location m bit. So there are 2 to the power of n address locations, and each address location contains m bit. So the total memory size will be 2 to the power of m, 2 to the power of n into m. This is how we derive it. So the correct answer is B. Right, this is the derivation. So if you have any doubt, you can ask regarding this. Yeah, so it is given the memory has n address lines. What does n address line means? Therefore, that each address location can be identified using an n bit string, you can say. So if there is it is n bit address lines, so how many address locations can be represented using that? It will be 2 to the power of n. Each address location will have a unique n bit address line. Now it is said there is m data lines. Now m data bus means each address location has a size of m bit. Therefore, there are 2 to the power of n address locations, and each address location contains m bit data. So total memory size will be 2 to the power of n, that is the number of address locations, multiplied by m, that is the size of each location. So that will be the total memory, 2 to the power of n into m. This is the derivation for this. I know in the slides it is given as formula, but this is how it is derived. Okay, so let's go to the next question. So which of the following statements are either or false? So try to solve it. You can write the answer on the chat. I will respond. So the question is, which of the following statement is or are false? So number A is a volatile memory lost when power is switched off? Option B is dynamic memory requires periodic refreshing. Option C is magnetic tape does not allow random access of data, and option D is none of this. So let's go one by options on one by one. So option A. So in a volatile memory, data is lost when power is switched off. Yes, this is correct. This is true. So why it is true? Because it is a CMOS circuit, so it is not able to restore the data. And typical examples are SRAM, that is your cache, and DRAM, the one memory that is there in your computer. Option B is dynamic memory requires periodic refreshing. Again, it is true. Uh, if you ask why, what is a DRAM? So a DRAM consists of a transistor and a capacitor. So data is stored in this capacitor, in form of charge, so it requires refreshing. A capacitor does not, if you have like, if you have gone through like the physics, in physics, primary physics, you know that capacitor does not hold on to the charge, so it has to be required to so it has to be refreshed from time to time as a result, so that the charge is hold. So dynamic memory requires periodic refreshing, so this part is true. Option C. Magnetic tape does not allow random access of data. Again, this is true, because in a magnetic tape, you need to just move to the particular location of where the data is stored, because here the memory access is sequential. So a magnetic tape, here the memory access is sequential, so it is not, the data is not in a random access mode like that is in some like SMOS or DRAM or SRAM. So the correct answer is option D. All of them are true. Right. So if you have any doubt, you can ask. Okay, so let's go to the next question. So again, you can write the answer in the chat. I will respond. So question 4 is, which of the following which are false for cache memory? It consumes lower power compared to main memory. It is a type of non-volatile memory. It decreases effective speed of the memory system. All of this. Why C? Why C? If C is true, then why are you using cash? Right? If C is true, why are we using cash then? Then no need to use cash only. Okay, this is very straightforward. A is true. No, A is false. Sorry. It consumes the most power. It is a type of non-volatile memory. No, it is a volatile memory. Uh, just like your RAM, it gets it is not, the data is not restored once your computer or PC or laptop is rebooted, or even mobile these days. It decreases the effective speed of the memory system. No, it increases the effective speed of the memory system. So the cache works like this. This is the CPU. This is the cache, and this is the memory. So cache is faster than the or any other form of memory. So how does cache work? So when a CPU fetches a memory like a memory chunk from like wants a data from main memory or secondary memory, so it first asks the cache whether that data is present in it or not. So if it is not present, then only it fetches the main memory to check if it is there or not. So as a result, the main reason as a result, the main reason for having cache is that these memory access time is very fast, right? This memory access time is very fast. So so as a result, whenever it mm, uh, so whenever it first fetches a data which is not present in the if it wants to fetch a data for its program, it first asks the cache it is there or not. If it is present in the cache, then it goes for it is not present, then it goes for the main memory. So as a result, it the access time is decreased. So access time gets reduced due to cache. Right. So C is true. It reduces the effective speed of the memory system. So the correct answer is A and B. So any doubt regarding this? Any doubt? Okay, so I will move to the next question then. So the total number of external connections required by a 8 cross 8 memory will be. So what is the total number of external connection that will be required for a 8 cross 8 memory? So let's solve it. So we have 8 cross 8 memory. Let's put one here. 1, 2, 3, 4, 5, 6, 7, 8. So these will be the 8 cross 8 like memory, if you ask. So there will be 64 such places like at memory locations. Now how to generate these address locations for each one of them, right? How? So if we, for that we require, these will be 8 lines, right? So you required a decoder. So you required a 3 cross 8 decoder. So that means using 3 address lines, you can you can address each of these memory locations, each of these columns, each of these rows, memory rows, right? And, the next will be like you need to address data from each of them, each of these columns. Here will be, there will be the special connections called the data output points. This is called data output. So there will be 8 such connections for data output, 8 such connections for data output here. So so there will be three, here is 3 external connections, here there are 8 external connections. Other than that, there will be 2 more external connections for read, write and clearing the memory, and for choosing whether it is a read or write connection, and 2 more will be for power and ground. That is very common for any MOS circuit, CMOS circuit. So what will be the total connections? 3, 8, 2 plus 2. So it is 3 plus 8 plus 2 plus 2. So total it will be 15. 15 is the correct answer. Shall I repeat once more? Yeah, so if you can like if you have gone through the lecture, you know that each the memory connections, so for a 8 cross 8 memory there will be 6 total 64 memory cells. So that will be located, so 8 cross 8 means there will be 8 rows and 8 columns. Now we need to find out like how many external connections are required for this to access this memory. So to access each row we require total, how many, there are 8 rows, so you require 8 lines. how can we access 8 lines, 8 of these lines? 8 of these lines can be accessed using like 8 of these lines can be accessed using a 3 cross 8 decoder. So that means using 3 external connections, which is equivalent to 2 to the power of 3. So this is a 3 cross 8 decoder. Using a 3 cross 8 decoder, we can generate total 8 such control signals to access each memory location, right? So first these 3 is okay. Now you need to find out the data from each such columns, right? So how you can do it? Using, you need, for each column you need one data output channel. So there will be total 8 such external controllers of data output. So that is 8, right? Next, what we need, we each memory controller, each memory has two read write control signal and a clear state control signal. So either if read write is 0 or 1, it indicates it's a read or write operation, and clear state means it changes the value in the memory location to 0. So that is the two signals, and other than that it requires a power and a ground signal. We all know what power and ground means from that due to the transistors. So in all we have 3 from this decoder side, 8 from this data column side, then 2 for this read write and CS, and 2 for this power and ground. So so total it will be 3 plus 8 plus 2 plus 2 equals to 15. So if it is any random question, like if it is given as suppose 64 cross you have been given a this memory location 64 cross 16, right? So what it will be? Can anyone do it? Just do it, right? It is very easy. So if you have, if in the question you have been given a 64 cross 16, what will be the memory connections? Please try this, you can do it, like you can write the answer correspondingly in the chat for a 64 cross 16 memory. So, it will be, yeah, correct, right, it is, yes, it is 20, it will be 26. So like similarly, like how I did it. So for 64 it will you will require uh, 6, 2 to the power 6 is 64. So you require 6 such 6 cross 64 decoder. So this one will be 6 plus, here from here 16 will come, right? Plus these two and these two will be always same. So it will be 26. Yeah, good, you have done it. Okay, so I will next go to the next question. So the question is, which of the following is or are true for virtual memory system? So which of the following are true or false for the virtual memory system? So option A is it increases the size of the program that can be run. Option B is it increases the size of the physical memory. Option C is it increases the size of the secondary memory. Option D is it improves the processor memory bandwidth. So which will be the true of this? So option A is true. It increases the size of the program. One of the reason is what does virtual memory does is virtual memory, if you have gone through the text, it basically means that part of the secondary memory is considered as a part of the primary memory, so that for basically parallel processing of much more processes. So option A is true. So virtual VM only increase the size of the memory. VM increases the size of the memory that can be done. Option B, it increases the size of the physical memory. No, physical memory size remains same, but it uses, but it allows that, uh, but it makes sure that some part of the physical memory is used while the program is running. That means if part of the program that is running are stored in the physical memory, which is not currently is required. Option C, it increases size of the secondary memory. Same, false. Secondary memory, no question. Physical memory is not its size is not increased. It all remains same. Option D, it improves the processor memory bandwidth. Again, it false. These all things remains constant. Size of the physical memory constant. Size of physical memory and secondary memory processor memory bandwidth. It only increases the size of the program, and that is also necessary because the program has to be stored partially in this physical memory when it is running, and partially in the main memory when it is being done. So the correct answer is option A. So let's go to the next problem. Which of the following statement is true for writing 1 in SRAM chip? Bitline B is set to 1 and bitline B is set to 0, and these are the 4 options. So let's discuss about what is an SRAM chip and how does it looks. So you have a circuit like this. This is connected to a transistor, and this is connected to a transistor. This is transistor T1 and this is transistor T2. Now it is connected to these two bit line. So this is B and this is B dash. So these are two bit lines. Now you see to write 1 in this SRAM cell. This is an SRAM cell, right? This is an SRAM cell. So to write 1 in this SRAM cell, bit line B will have to be set to 1 and B dash is set to 0. This is to write 1. And B is equal to 0, B dash equals to 1 to write 0. So then which of the following option is correct? If this is the like this is a theory, so which of the following option is correct? Option A says the bit line B is set to 1 when bit line B and bit line the B dash is set to 0 to write 1. So option A is true. Option B, bit line B is set to 0 and B dash set to 1 to set sorry, 1 minute. To write 1, bit line B is to write 1, bit line B is set to 1 and B dash is set to 0, and bit line 0 and bit line B dash is 1 for to write 0. So A is set, bit line B dash B is set to 1 and B dash is set to 0 to write 1. That is true. Option B says B is set to 0, B dash is set to 1 to write 1. It is false. C, it's not possible. B1 1 and B dash 1. This is also false. D is also false. So the correct option is option A. Right, so let's go to the next problem. If you have any doubt, you can ask regarding this. Okay, so let's go to the next problem. So we have been given a 1-bit memory organized as 1024 rows and 1024 columns. Each data bus has 16-bit wide. So total number of address lines required will be we have a memory which has 1-bit memory which has one m-bit memory is, that means is 2 to the power of 20. 1 m-bit memory. Now it is said that data bus width is 16-bit. Data bus width is 16-bit. And there are 1024 rows. So it will be 2 to the power of 10, right? So this can be written as 2 to the power of 10 cross each data bus is 16 bit wide. So if it is 16, we can write it as 2 to the power of 6 into 2 to the power of 4. Okay, so since each memory location is 2 to the power 16 bit bit, so it is 2 to the power of 4. So this is how the 2 to the power of 20 can be written. So it is told number of address lines. So to address each column row, to address each row, we required 10 10 lines, right? And this is the location of, so if we can visualize it, so this is each row address and this is the location of each row. This is the data inside each row. So this width is 16, right? So if this is 16, so how many such column will be there? So if this is 16, that means 2 to the power 6 is left. So there will be 1, 2, 3, 1, 2, 3, 4, 5 and 6 such columns. So it will be 10 plus 6 from here, 6. It will be 16. So correct answer is option A. So I will repeat again. So it is given 1 bit, 1 M bit memory is organized as to the power of 1024 rows and 1024 columns. So here will be 1024 columns and 1024 rows. Now it is said that the data bus width is 16. So it can be written as 2 to the power of 10 into, this is the data bus width, like 16, and so how many bit left? 6 bit, right? 10 and 4 are gone to 6. So there will be 2 to the power of 16, 2 to the power of 6 as data bus. So the total number of external connections required for this will be 10. So we will use a decoder. So using 10 bit width, we can find each such row and 6 for each column. So it will be 10 plus 6 equals to 16. So correct answer is option A. Any doubt regarding this? Okay, so let's go to the next question. So it is given, sorry. So this will be actually, I misrepresented it. Okay, sorry, it will be 280. So it is given for a DDR2 SDRAM if the internal clock is 480 MZ and bus clock is 280 MHz, what will be the maximum data transfer? So if you have gone through the lecture, so there is a formula for finding this. So it is 2 into bus clock plus bus clock frequency into 10 to the power of 6 into 64 divided by 8. So if you put the value here, so and this uh, the unit is always GB per second. So if you put the value here, it will come out to be 4.48 G per second. So this is a very standard formula question. So for this purpose, you need to remember it. This, I mean, there are no other options other than this option C. So this is the formula to find max data transfer rate. Okay, so let's go to the last question. Consider a memory chip with size 1 GB byte, and there are four such chips, large such chip. They are connected together to a large byte-oriented memory system using memory interleaving, where the processor data are 32-bit wide. If there are four such chips, M0, M0, M1, M2, M3, which memory address module will be with the memory address this and this map to. So I will explain it in quite simple terms. We have a memory chip, one memory chip, one GB. So if we write it in terms of bits, it will be 2 to the power of 30. So there are 2 to the power of 30 locations. Now let's say it is given for such, like it's 2 to the power of location, such memory chip. So how many such locations now it will be? 4 into 2 to the power of 30, that is 2 to the power of 32. It is given, see, it is given processor data width line is 32-bit, 32-bit wide, it is given. So now how it is being used? So here is one chip, suppose it is M0, M1, M2, M3, right? Now the what it is being, how it is being accessed, if I explain it in simple terms. So there is a mux. So this is a 2x1 mask. What does a mask does? It takes two signals, M0 and M1, and it produces four control signals, right? One minute, let me rename it. So let me rename it to A0 and A1. So these are the two control signals using which we can access any one of the memory chip, and each of this memory chip has a 30 bit 30 locations, like 30 address locations, 2 to the power 30 address locations. So to access each one of them we need 30 length word. So it will be A2 dot 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 A2 A3 dot 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 A31. So these 30 address are used to represent any byte inside this memory or this memory. First two bits A0 and A1 are used to address which of the memory that is to be used of this chip, either it is M0, M1, M2 or M3, and the rest 30 are used to find address in that specific memory. So it is given which which of the memory chip does this goes, like this addresses goes 0501 this, and this which of this memory chip does this address go. So let's take the first one, 0 5 4 2 3 6 4. These are hexagon numbers. A. So the last we are concerned with only the last two bits. So what does A represents? 1 0 1 0. So let's say so how does it here? So if the A0 A1 is 0 0, it goes to M0. If it is 0 1, it goes to 1 1 M1. It is 1 0, it's going to M2, and 1 1 it goes to M3, right? So here what is the value of the last two bits? 1 0. So if it is 1 0, where does it goes? It goes M2. So this address will be present in M2. This is referencing an M2. Now for if we say A54200C, what it will be? Can anyone tell? Which one it will represent? How M4? What is C? Yes, if it C, so then what it will be? If the last two bits, what are the last two bits? 0 0. So it will be M0. So what does C represents here? C represents 1 1 0 0. What is 0 0? 0 0 is M0. So it will be M0. So the correct answer is option B. Shall I repeat this one again? Or it is clear? Okay, so I will repeat once more. So it is given there is a memory chip whose size is 1 GB, and there are 4 such memory chips of 1 GB. The processor data bus is 32-bit wide, and there are 4 such chips, M0, M1, M2, M3. So where does this this address and this address map to which chip? So one memory chip is 1 GB, that is 2 to the power of 30 locations, right? So 2 to the power 30. So and there are 4 such memory chip, that is 4 into 2 to the power 30. The total addresses will be 2 to the power of 32. it is also given that 32-bit wide each. So now how can one access each of these 4 chip one at a time? It has to be like using these two, using a 2x1 mask. So this 2x1 mask, there will be two signals that will be required, two address will be required for this 2x1 mask, A0 and A1. So it will, so A0 and A1 are the two address lines extra. So and this each will require a 30-bit address, A2, A3, A3 dot A31. So if it is 00, it will represent M0. If it is 01, it represents M1. If it is 10, it represents M2. And if it is 11, it represents M3. Now you see what this address represents. There is this address given 05423648. This is a hexagon number. We are concerned to map the chips, we are concerned only with the last 2 bits, that is last 2 bits of this A, that is 1010. So what is the last 2 bits? 10. What does 10 represents? M2. So this address 05423648 represents M2. Now if we consider this address 1A54200C, what does the last C represents? 1100. So what are the last 2 bits? 00. What does 00 represents? M0. So the correct answer is B, M2 and M0. Clear? Okay, so this was the last question. If you have any doubts regarding any of the question, you can ask. Four K is like if you, so in terms of the K, in terms of memory, you can say it is 2 to the power of 10, right? Yeah, so 1 GB, like if you have attended the first one, like the lecture, like first session I took, there are this thing I have taught, like so like 1K is 2 to the power of 10, 1 M is 2 to the power of 20, and 1 G is 2 to the power of 30. So there K is basically like if you like in terms of 100 it is called 1000, K is 1000, but in terms of this byte arithmetic and these things, these are 1024. So what is 1024? 2 to the power of 10. So there, that is the K. Okay, so that was the last question. So we will again meet next week at Tuesday 6 p.m. So thank you for attending.